Okay, hi everyone, I'm Melissa Diamond. I'm a postdoc from Queen's University, so we're continuing the Queen's University streak. And today I'm going to be talking to you about using fireballs to detect or look for exotic particles. This is based on these papers here, as well as some ongoing work with all of these wonderful people. So, at this point, after all of yesterday's talks, I think we've clearly established that hot neutron stars are a really powerful tool in exploring dark matter and other beyond the standard model particle theories. When I'm talking about hot neutron stars, I'm specifically referring to two different scenarios. One is binary neutron star mergers, and the moments immediately after the merger, focusing on the remnant that gets left behind. Oh. Thank you. The other object that I'm interested in are core collapse supernovas. These are the supernovas that lead to the production of neutron stars and the protoneutron star in the core of those objects. So both of these are fairly similar environments. They're both incredibly dense and very hot with temperatures exceeding 30 MeV. And this is really what makes them great places for producing large fluxes of exotic particles, dark matter or not. And that's because these can thermally produce particles with masses up to hundreds of MeV and couplings to the standard model that are weaker than neutrinos. So this is the sort of parameter space that we get to explore and that are produced in large fluxes in these environments. All right, so this is a useful tool. The question is, what then do we do with these large fluxes of exotic particles, assuming they exist? How do we look for them? How do we make any sense of that? Well, one option is to look for particles whose coupling allows them to escape the hot neutron star environment and somewhere in flight between the neutron star and the Earth decay back to the standard model. Now, particles that can do this aren't going to make for very good dark matter candidates themselves, but they can play key roles in mediating interactions between dark matter and the standard model. For this talk and for the work that we've been doing, I'm going to be focusing on particles with masses in the MeV to GeV range. The GeV being the upper limit because the temperatures inside of these hot neutron stars are not hot enough to really make anything heavier than that. And then the lower limit is because for the effect I'll be talking about for creating a fireball, we need particles that can decay and produce electron-positron pairs, and they have to be at least this heavy for that to be possible. Now, I'm going to be focusing on axions. All the effects that I'm describing today are really not limited to axions. You can insert your favorite BSM particle in the right mass and coupling range here, and it'll work just fine. But for a concrete example, we'll talk about axions. When I'm talking about axions, I really mean axion-like particles. I'm referring specifically to a massive pseudoscalar which couples to, effectively, E dot B. And this will allow it to be thermally produced inside of neutron stars and will also allow it to decay into 2 photons before reaching the Earth. So that's the specific variety that we're interested in, which sort of pushed the wrong button. So that's going to put us in the 10 to the minus 9 to 10 to the minus 10 inverse GeV coupling sort of range. All right, so we've got a source. I'm telling you that if axions exist, if they're in this mass range, these sources can make a lot of them. Then the question is, what do we do with that information? How do we see it? And this is where the fireball comes in. So starting from the source, we've got our hot neutron star, and it's just radiated off a bunch of axions. They escape, and somewhere in space on the way to the Earth, they're going to decay into, in this case, gamma ray pairs. What happens next is going to depend on how many axions we started with and exactly where that decay takes place. If we end up with a fairly diffuse shell of photons, then the photons that are produced end up simply freely escaping to the Earth, and they leave with about the same energy that they had, that the axions would have carried when they left the neutron star in the first place. This is sort of the most straightforward picture. However, if the plasma shell formed by the photons happens to be dense, then what can happen instead is that we can get all of these photons scattering off of each other and pair producing. Once this happens, we don't get free streaming anymore. We instead get something called a fireball, and the fireball is going to very much change the types of signals that we can look for. So a fireball is an opaque, thermalized, expanding shell of photons, electrons, and positrons. Essentially, the photons and electrons are scattering too quickly. Their scattering length is short compared to the thickness of the shell, and they're not free to escape. Instead, what happens is, in scattering off of each other, the kinetic energy of the gas is going to drive the expansion of the shell, causing it to accelerate relativistically until it becomes either cool enough that pair production of electrons and positrons turns off, or diffuse enough that the photons can escape. Regardless, what will happen is we'll end up with significantly more photons than we started with, and at significantly lower energy than they would have had otherwise. So in terms of what we're expecting to see, again, energies are significantly reduced. We're expecting a signal more around 100 keV versus, in the free streaming case, just tens of keV. And then in terms of giving some description of what we're looking for, you can expect that this will be a signal which is thermal and boosted. It's thermal in the gas frame. The gas frame is accelerating toward us, so it's boosted from that perspective. And it's isotropic. For differentiating this signal from other more typical astrophysical signals that we might expect from, say, a neutron star merger, we can rely on things such as the total energy being carried off by the axions, exactly where that energy spectrum lands, and when the signal arrives to us and how long it lasts. These are all predictions that you can make based on your specific axion model, and then one can compare these against observations or make predictions for future neutron star mergers and then compare this against what we would expect to see. So this has all been a bit theoretical, so now let's actually talk about what the impact is on existing constraints and what we can hope to do going forward, what parameter space we hope to be able to explore with this. So first, let's look at some existing axion constraints. So down here is the axion-like particle mass in MeV. Over here, this is its axion proton or photon coupling in inverse GeV. And this whole big gray region here is parameter space, which has been ruled out based on observations of gamma rays from supernova 1987A. Now, the way that these original constraints worked was basically the free streaming case I described to you just a few slides ago. The axions were made in the supernova core, they escaped, they decayed into gamma rays somewhere between the Earth and the supernova, and then we saw those gamma rays, or we didn't. And all of this parameter space would be ruled out because we didn't see those gamma rays. Now there is one complication here, which is that this signal depended, or this observation required that all of the gamma rays reaching Earth have at least 25 MeV of energy. That was the minimum energy that the solar maximum telescope could see at the time. But as it turns out, in this entire sort of highlighted in black region here, this is where, given the conditions that led to this axion production in the first place, those axions, when they decay, would have led to the production of a fireball. And that would have significantly reprocessed the photons and very much reduced their energy. So actually in here, any of those gamma rays that were originally emitted by the star would no longer be observable because they would have fallen below 25 MeV. Fortunately, there was another telescope that happened to be floating around at the time that was sensitive to X-rays, the Pioneer Venus Orbiter, and this was able to see photons in the energy range as they would have been because of the fireball, and didn't see anything. So we haven't quite ripped open parameter space here for axions, but what we've ended up doing is predicting a different signal than the original one, and then using a different observation to constrain that. So what I'm just hoping to demonstrate here is that if you're interested in producing large numbers of particles from a compact source, and if those particles can interact with themselves, or they can become standard model particles, which can interact with themselves, then it is important to consider this fireball effect, because it may very much change the signal that we end up getting at the end of the day. Now looking forward, the fireball's not always a bad thing. It actually may help us explore more parameter space more easily. Nowadays, our coverage of the 10 MeV sky is not quite as good as our coverage of the 100-ish KeV sky. And so the fireball actually is helpful in bringing signals down into an easier to observe part of parameter or energy. So over here, this is a soft sense of what we expect to be able to see or constrain in the future based off of observations of the binary neutron star merger GW 170817. So again, down here we've got the axion mass in MeV. Over here it's coupling to photons in inverse GeV. And there's two sort of sets of regions I've marked off here. The orange one is where, based on the number of axions we might have expected to be emitted by GW 170817, we would expect a fireball to form. The blue region here, this is where the total energy carried off by the axions is equal to or greater than the energy observed in the gamma ray burst associated with this neutron star merger. So putting these two together in this sort of blue and orange striped region here, this is where we could get a signal that is more energetic than the actual gamma ray burst associated with this merger, that also is in about the right energy range, or about the same energy range as the merger, or as the gamma ray burst would have been. So we're still refining this a bit, but this is an idea of what parameter space we expect to be able to potentially exclude, or at the very least explore more carefully going forward. And you see we've got two different sets of lines here. So this is just because we are looking at two different equation of states for the merger, or for the remnant left behind from the merger. And I'm just showing you the more conservative set of the two. Okay, so what I hope you take away from this talk is that one, hot neutron star transients. Okay, cool. Hot neutron star transients are a great source of light beyond the standard model particles. In particular, we focused on axions, but you don't need to confine yourself to axions. But we can get observable signals based on these objects escaping from these hot transients. What exactly that observable signal looks like is going to depend pretty carefully on whether or not a fireball forms. So any analysis that takes this sort of approach does need to consider, does a fireball form, and what does this do to my end observables? And then looking forward, our expectation is that as modeling of neutron star mergers of core collapse supernovas improves, as we see more of these events, we'll be better equipped to explore more parameter space for axions, dark photons, and any other sort of exotic light particles in this mass window. Thank you.
Thanks for the nice talk. I was wondering if you could talk a little bit about the production mechanism for the axion in the neutron star.
Yeah. So we're assuming two different production mechanisms. So there's photon coalescence. Actually, I might have a slide for this. Oh, yeah, right here. Okay, so we've got photon coalescence, which is just the reverse of this plot here, two photons crashing into each other and making an axion. And then we have the Primakov process, which is the photon is scattering off of a charged nuclei and becoming an axion. I believe this is the dominant process at lower masses, and the other is dominant at higher masses, but I might have those backwards.
All right, thanks.
Another question? Okay, so let's thank our speaker.